this lessons, we are going to look at the different equations that are dealing with gas molecules. But before we start talking about those equations, let's review about kinetic energies, because kinetic energy is talking about gas molecules. Now, kinetic energy is represented by Ke. So, a kinetic energy of a particle is equal to 1/2 times the mass times the velocity to the square. Now, mass is represented by m. Okay, so if you notice, look at the m. M is directly proportional to the kinetic energy. If we increase in m, guess what happened to the kinetic energy? It also increased as well. And then we have v. V is your velocity. Now, velocity, think of velocity as the speed or the molecular speed of the particle. And the same thing, if you increase v, guess what happened to the kinetic energy? It also increased as well. Then we have the term average kinetic energy. Think of the term average. This is talking about the kinetic energies of a samples of a gas, okay? And basically, we use an instrument that measures the temperature of a sample. And what's so special about average kinetic energy? And that is, the average kinetic energy is directly proportional to temperature, which we can measure with a thermometer. We cannot measure average kinetic energy, but we can measure temperature. So if temperature go up, it is directly proportional. That means the average kinetic energy also go up as well. That means if you have a sample of gases or a mixture of gases or a mixture of different gases at a temperature, at a given temperature, all those gases molecule will have the same average kinetic energy, and that's important. Now let's talk about the first gas law, and that is the Dalton Gas Law. And Dalton Gas Law states that the total pressure of all gases, okay, in a mixture of gases, different gases, or the same gases, doesn't really matter, is equal to the sum of the individual pressure of all gases. And basically, what does that mean? Is that the total pressure of all the gases in that container is equal to the individual pressure of A plus the individual pressure of gas molecule B and plus the individual of gas molecule C, and so on and so on. And we're going to talk about this specific equation more in detail when we work with the problem. But using this knowledge, we can actually relate this to the partial pressure. Now, partial pressure is talking about the pressure of a specific molecules or specific gas in a container. And that partial pressure is equal to the total pressure multiplied by the mole fraction of that gas, either A, B, or C. And to put in mathematical term, we have this right here, PA. This is referring to the partial pressure, okay? PA, or PB, or PC, this really matter. And to find the partial pressure of A in that container, you take the total times the fraction. Now, this is where we get a little more tricky, is that this fraction right here, this mole fraction, think of the word fraction. Fraction is always part over total. So in this case, the top part will always be the part. And what is the part that we are looking at? It is the exact number of moles of that specific gas molecule and over the total. In this case, if we look at this example, we have A, B, C. Those are the three gases. For the total would be the total number of moles of A, B, C. Now, if I want to look at the partial pressure of A, I would have the number of moles of A's on top. If I want to look for B, the B would be on top, and so on. And that's how fraction works. We can change the part relative to the same total, and it works the same thing. And lastly, we have this equation called the ideal gas law equation, and that is PV equal to nRT. P is for pressure, V is for volume, equal to N, that is the number of mole, R is the universal gas constant, And on the back side of your periodic table, there are multiple R constants. Make sure you use the right one. And how do you know? Is that you look at the R with the unit that's involved in this equation. And basically, let's talk more about this equation. What's so special about this? Well, with this equation, now you can solve for any variable in this equation. When we can just use the R constant from the backside of the periodic table with the assumption that all the other variables are given somewhere in the problems, okay? So what are the unit in this equation? Well, P is in ATM, that's atmosphere. V is in liter, okay? And N is in moles. And this one, T, which is your temperature, it is going to be in Kelvin. Now let's go back to our periodic table. Well, there are multiple gas constant, and the one that has ATM, liter, moles, and Kelvin, and that would be this one right here, 0.08206, and that would be liter times ATM divided by mole times Kelvin on the bottom. And you see how all the units are given in this equation right there, okay? So that's how you know which R constant to use. Now let's look at one sample problem using all the information we just provided up here. A student placed 7.5 moles of sample of methanol, CH3OH, in a rigid container. That means it doesn't expand, it's rigid, it's fixed, it's super hard. Container of 15.0 liters. So this container has a volume of 15.0 liter. And we're going to heat this container to 325 degrees Celsius. Now, be careful. This is Celsius. What do we have to do when the temperature is not in Kelvin? We have to convert this to Kelvin. And basically, we take Celsius plus 273, that gives us Kelvin. So always convert to the right unit, okay? And at this temperature, some methanol decomposes. Like I said, methanol decomposes into carbon monoxide gases and hydrogen gas. At equilibrium, we have 6.0 moles of carbon monoxide are found in the container. Basically, this is how much is being produced right there. Okay, so with this information, let's solve this problem. The first one we have is determine how many moles of hydrogen gas. Well, remember this is a balanced chemical reaction, so all you have to do is use stoichiometry. In this case, we have 6 moles at equilibrium, okay, 6 moles of CO2, okay. Well, at equilibrium, we have 6 moles of CO. So here we have 6 moles of CO. And then, all we have to do is using a balanced equation and convert to moles of hydrogen. Well, in this case, what's the coefficient for CO? That's just 1. So we have 1 mole of CO. And on top is hydrogen, which is 2 moles of H2. And look what happened to the moles of CO. It cancels out what is 6 times 2 moles of hydrogen. So we have 12.0 mole of hydrogen gas. And that is how much hydrogen gas is in this container at equilibrium. Isn't that easy? Next, let's determine how many moles of methanol are remaining at equilibrium. Now this is a little bit tricky because we initially have a specific amount of methanol. And we need to determine the difference of the initial and how much is being used to determine how much is remaining. So initially, we have 7.5 mole of methanol, CH3O, okay? And to find how much is remaining, we are going to subtract how much is being used or reacted in this chemical reaction. In this case, the word is decomposed in this chemical reaction, and that will give us our remaining CH3O, okay? So the tricky part is how we determine that. And the same thing using stoichiometry. Given the fact that we have 6 moles of CO, so let's look at this. We have 6 moles of CO. Okay, let's change this to different colors. So that way we don't get confused. And 6 moles of CO times the ratio. What is the ratio? 1 to 1. So we have 1 mole of CO, and that is relative to 1 moles of methanol, CH3O. So this cancel out. We have 6 moles of methanol is being used in this chemical reaction. So now we can plug this in here, okay? We can plug this in here. So now it's going to be 6.00 moles of CH3O being used. And what is 7.5 minus 6.00? And that turned out to be, easy math, 1.5 mole of CH3O. There you go. And that is how much CH3O is remaining in the container after being decomposed into carbon monoxide and hydrogen gas. And the next one is determine the mole fraction of carbon monoxide, which is CO, in the tank. So this is mole fraction for carbon monoxide, CO. And again, it's part over what? Total. Okay? So in this case, we're talking about in terms of moles. Everything in chemistry is relative to mole. You have to keep that in mind. So what is the number of moles of CO? Well, we are given in the problem here, which is 6. So in this case, we have 6 mole of carbon monoxide. Now, I'm going to divide by the total. Now, the total would be relative to what? The moles of CO plus the mole of CH3O and plus the mole of hydrogen. Because those are the only 3 gas in the containers. Now, we know this right here. Let's change to a different color first. We know that for CO, that would be 6.00. We know that, and we also know that the remaining methanol left in the container is 1.5. And we also figured out that it's 12 moles of hydrogen that's being produced. So what is the total in this case? So we have 6.00 divided by 6 plus 1.5 plus 12. And that is what? 19.5 right there. And that would equal to what? We have 0.308. Okay, and that is the mole fraction for carbon monoxide. Let's go to the next one. Determine the total pressure. And that's talking about all the gases in the container, okay? In ATM, in the tank at 325 degrees Celsius. Well, remember, we have PV equal to nRT. This T must be in what? This T must be in Kelvin. So we need to take this plus 273. So we take 325 plus 273. And if you don't remember if it's 275 or 276, look at the back side of your periodic table. It's given to us. Kelvin equal to Celsius plus 273. So in this case, our Kelvin in terms of temperature is 598 Kelvin. So let's plug this in. Well, in this case, we're solving for pressure, right? So PV equal to nRT. So now is, of course, P is equal to nRT divided by V. And we know our total mole is right here. This is our total mole right there. So that is 19.5. And the R constant we mentioned before, it is 0.08206. And what is our temperature in this case? It is that value is right there. It must be in Kelvin. So 598 K. Notice I didn't write any unit down there because I want to simplify the math and I don't want to be confused by those variables. Okay? So in this case, I divide by my volume, and the volume of the container is what? It is 15 liters right there. So now I just put this in 15 liters. So let's solve this in a calculator. 19.5 times 0.08206 times 598 divided by 15. And what do we have? Our pressure is equal to 63.79 atm. Whoa, that is a lot, okay? Well, it doesn't matter. This is a hypothetical problem, okay? But that is a huge amount of pressure. Now let's go to the next problem. Determine the partial pressure of CO in the tank. And we remember that the partial pressure is equal to what? P total times the mole fraction. In this case, the P total, which is, let me just write it out for you. P total times the fraction of CO. And that turned out to be, this is your P total right here. okay? And that is 63.79 times what's the mole fraction for CO? And we just figured that out right here. It is 0.308. And that turned out to be, we have 19.64 atm. Now let's continue to solve the next problem. Determine the partial pressure of hydrogen in the tank. And the same thing in this case is pH2, and we're looking at P total time the mole fraction of hydrogen. Well, do we know the mole fraction of hydrogen? No, we don't, but we can use the same concept right here. So in this case, this can be, look at this right here. So how many moles of hydrogen do we have? We have 12 moles of hydrogen divided by the same total number of moles, which is 19.5, and 12 divided by 19.5. This gives us 0.615. So now we have the P total, which is 63.79 times 0.615. And this gives us the partial pressure for hydrogen turned out to be 39.26 atm. Ooh, that's a lot of pressure. Let's move on to the next problem. How do the average kinetic energies of molecules of gases compare? Basically, what are the average kinetic energy of different gases? In this, how are they compared to each other? Because they are at the same temperature, they would have the same average kinetic energy. And lastly, which gas in the container has the highest average molecular speed? And we are talking about the gases methanol, carbon monoxide, and hydrogen gas. And of course, the one with the highest speed would be the one with the smallest mass. And that is what? In this case, is gonna be hydrogen. If I ask you which one would have the slowest molecular speeds, that would be methanol, and so on. Isn't that easy?